In section 4.6, we're going to look at change of basis. So we know that there are spaces with multiple bases. In fact, most spaces have multiple basis vectors that we can use to represent them. Okay, so let's start off. I have two bases here. So I have a basis B, consists of vectors B1 and B2. Okay, so it's a two-dimensional space because there's two basis vectors. And then I'm going to have a basis C that has vectors C1 and C2. Okay, so given B and C are bases, remember the plural of basis is bases, for vector space V. Okay, maybe it's an R2 vector space, maybe it's P1, something like that, but two-dimensional vector space. Okay, so let's give some details about this vector space. So I have a vector X that's equal to 3B1 plus B2. Okay, and the same vector X, again, this is X, okay, same X on each of these, is also equal to 6C1 plus 4C2. Okay, now we know from our last discussion of coordinates in 4.4 that these linear combinations generate our coordinate vectors. Okay, so I know that the coordinate vector for X with respect to B, basis B, is equal to 3, 1. Again, that's those coefficients, right? Those are our scalars that it's multiplied by. And I also know that the coordinate vector of X with respect to basis C is equal to 6, 4. Okay? And so I want to be able to go between those, okay? Now, visually, to get the idea of what we're looking at, I'm going to borrow the book's picture here. All right, we can see that the vector X along this picture is in the same spot relative to the origin. Okay, but we take two different paths to get there, right? 3B1 and 1B2, okay, has a B2 vector going out this way. Or perhaps we take this path over here, which was 6C1 and 4C2, okay? But we get to the same location here for the vector X. Now notice too that the coordinates given are positive, even though the point here, X, may actually be negative, right? If I did this with the standard basis, I would have a negative value for the y coordinate, okay? So that is still a possibility. Your coordinates can both be positive even though the vector is negative, or vice versa. Your coordinates could be negative when your vector is positive, okay? Just depends on what the original basis vectors are, okay? Now notice we don't know what these basis vectors are, okay, to make this observation. So let's do some work here to look at changing between one basis to another basis, okay? So here's our example. I'm going to have a vector B1 is equal to negative 2C1 plus 3C2. Okay? I'm going to have a vector B2 that's equal to negative 5C1 plus C2. Okay? Where B is equal to B1, B2 as before, and then basis C is equal to C1, C2 as before, and they are bases of my vector space V. Okay, so I've got my vector space. I've got my setup here. Okay, I'm going to have a vector X that's equal to 3B1 plus B2. Okay, and we know from this information that the coordinate vector of X with respect to B is equal to 3, 1. Okay, that information is the same as we used there. Okay. But I have some information now about B1 and B2 instead of just having the information about X given to me. Okay, so our job is going to be to find this vector, this coordinate vector X in terms of C. Okay. Now, what is the coordinate vector X in terms of C? Well, it should be some type of unknown here. We're going to call them D1 C1 plus D2 C2. Okay. And I know I could set this up as a augmented matrix. If I knew the vectors, I would have C1 and C2 augmented with D1 and D2. Okay. Remember, this is a vector, D1, D2. Okay, and I could row reduce this and get that result. Okay, but I don't have that information. What I do have is I have information about B and C. Okay, so notice what I have here. I have the coordinate vector for B1 in terms of C. Okay, I know that B1's coordinate vector in terms of C is equal to -2, 3. And I also have that B2's coordinate vector in terms of C is equal to 3, not 3, -5, the wrong point, -5, 1. I have those coordinate vectors, okay? Now I know from what it means to be a coordinate vector that this means if I take C1 and C2 and augment B1, I'm going to get that coordinate vector. Same thing here, C1, C2, augment B2, that vector I'm interested in. So I've got B, but I want to go to C, okay? And I know I can row reduce this, and when I row reduce this, I will get the identity because I know these are independent because they're a basis. Remember, C is a basis, so I know these are independent. And what's left over here will be this identity vector, this coordinate vector. Okay, and then the same thing here. I'll get 1, 0, 0, 1 because it's independent, and I'll be left with B2 in terms of C. Okay? But this information I actually know. Okay? I actually know this information. I know what B1C is, and I know what B2C is. Okay? So I could do these together. If I took B1, nope, not B1. If I took C1 and C2 and augmented it with both B1 and B2, I could row reduce that, and I'll still get the identity here because it's independent. And over here, I'll get both of these coordinate vectors at the same time. Okay? Now consider these coordinate vectors are the solution to a system of equations. Okay? Two separate solutions to those systems of equations. So we know I have the matrix equation, right? I have AX equals B, our matrix equation that we're familiar with. So these vectors here correspond to a matrix that changes the basis. Okay? So my matrix here is going to be -2, 3. Again, that's my coordinate vector for B1. And -5, 1. That's my coordinate vector for B2. So I can write those coordinate vectors here, and if I multiply those coordinate vectors times my old coordinate vector, right? I know it in terms of B, 3, 1. I can multiply that by 3, 1. I know how to do matrix multiplication. This is -2 times 3 is -6. -5 times 1 is -5. Add those together, you get -11. In the bottom row, 3 times 3 is 9, plus 1 is 10. So I've got that vector there. And this is exactly the coordinate vector with respect to the matrix C, respect to the basis C, not the matrix C. Okay? Because those coordinate vectors correspond to exactly the same point. Okay? So I can take the basis, find the coordinate vectors, and then use the coordinate vectors to find the other coordinate vector. Okay? So we see we have these two matrix here makes a coordinate vector. Okay, so we're going to use a notation P, which I'm not always great at drawing, that this matrix goes from B to C. Okay, notice the arrow goes backwards. It goes from B to C. It points to the left, which feels kind of counterintuitive. We'll see why that is as we talk about finding change of basis matrices going forward. Okay, but if you know the coordinate vectors, right, I know, for example, that XC, okay, is equal to X, which is 3B1, B2. Okay, this was my original given definition for X. It was up here, X31B. But I need it with respect to C now. When I do that, I'm going to get 3 times B1's basis vector, or coordinate vector, and then B2's coordinate vector. Okay, so we can see this is the 3, 1 that's being multiplied by the 2 coordinate vectors I found. We're using that vector equation and that matrix equation in concert to write those change of basis. So if you know the coordinate vectors with respect to the other basis, which we did here, that was given. I know the B1 coordinate vectors with respect to C. You can use those to make a matrix, which is labeled as P from B to C. Use those coordinate vectors to make a matrix, multiply by the coordinate vector of what you're interested in, and that will switch you to the other basis. Okay, so that keeps us from having to first find it in terms of the standard basis and then convert the standard basis back to the new basis. I can just go straight from one basis to another. Okay, and again, I'll use the book's picture here to illustrate what I'm saying there. So instead of having to go from my original basis B up to the standard basis and down to my new basis, I can just go across the middle. Okay, and just go directly from one basis to the next. Okay, so if I'm looking at what we did here, I took C1 and C2, augmented it with B1 and B2. Okay, now here I knew the coordinate vectors already, so we didn't have to do the row operations to get these two vectors, B1 with respect to C and B2 with respect to C. Okay, but that same process will work to go between any two bases. Okay, so let's look at another basis here. Okay, so this basis is going to have B1 is equal to -9, 1. B2 is going to be equal to -5, -1. C1 is going to be 1, -4. And C2 is going to be 3, -5. So I have my basis vectors here. So B1 and B2 clearly make a basis for R2. C1 and C2 clearly make a basis for R2 as well. Again, these are not multiples of each other, okay? Altogether, right, there's too many vectors, but separately, I know I have a basis B, B1, B2, and I have a basis C, C1 and C2, okay? Now, we know from what we talked about last time, if I'm looking for a change of basis matrix that goes from B to C, okay, what I do is I take my C1 and C2 and augment that with my B1 and B2, and I'm going to row reduce that. And when I row reduce that, I'm going to get the identity on the left. Again, it has to be independent because it's a basis. And on the right, I'm going to get the coordinate vectors. Okay, not X. B1 with respect to C and B2 with respect to C, which together will form this matrix that we're interested in, P from B1 to C, from B to C. I should not say this is equals, I want to say arrow. Okay, so that's what I'm going to get. I get I with this change of basis matrix. Okay, so that's why it's written B to C. So the basis you're starting with, B, goes on the right, and the basis you're going to, in this case C, goes on the left. Okay, so I come in here, I'm going to write down what this is going to be. This is going to be P from B to C. I write down my basis vectors. Again, B goes on the right. So C, I've got 1, -4, and 3, -5, augmenting that with my B vectors, -9, 1, and -5, -1. Okay. Now we're going to start simplifying. All right, I'm going to do 4 row 1 plus row 2 is going to replace row 2. Okay, make sure you do all the columns. So I'm going to get 1, 3, -9, -5. First row's unchanged. Going to get 0 here, 4 and -4 is 0. 12 minus 5 is 7. 4 times 9 is -36 plus 1 is a -35. 4 times 5 is a -20. -20 minus 1 is a -21. Okay. Now I can easily scale row 2, so I'm going to take row 2 and divide it by 7, and that's going to replace row 2. So row 1 is unchanged. Row 2 now, -5, -3. Okay, so my new pivot here is 1. I want to get 0 above it. So I need -3 row 2 plus row 1 is going to replace row 1. Okay, so row 2 now is not going to change. But row 1, okay, I'm going to get 1 and 0 is 0. 3 and -3 makes 0. -3 times -5 is a -15. Minus 9, that's a -24. Sorry, try that again. Positive 15 minus 9, that's a +6. There we go. -3 times a Negative 3 is a positive 9. 9 minus 5 is going to be 4. Okay, so I've got 6, 4, and negative 5, 3 as the rows of my matrix. Okay, so if I have a coordinate vector, okay, coordinate vector x with respect to b is equal to 2, 1. I know that's equal to 2 times b1 plus b2. So let's fill in what b1 and b2 are. So b1 is 2 times negative 9, 1. And b2 is negative 5, negative 1. So I put all these together, I get negative 18 minus 5, negative 23. 2 minus 1 is 1. Okay? So the vector that I have to start with is negative 23, 1. Its coordinate vector is 2, 1. You can see why 2, 1 can be a lot easier to deal with. Okay? Now, if we look at it with respect to basis C, right? Again, x is the same. So I'm going to have d1 c1 plus d2 c2 is equal to what I just found for x, negative 23 times 1. Or negative 23 and 1. Okay? I can set this up as a system of equations. Okay? My system of equations is going to have c1 and c2, which is 1, negative 4, and 3, negative 5, augmented with what I'm trying to find, negative 23 and 1. Okay? So we're going to use our calculators, and we're going to row reduce this matrix. 1, 3, negative 23 on the top row. Second row is going to be negative 4, negative 5, and 1. We're going to row reduce that, and I'm going to get the identity because, again, that was a basis, so I know it has to be independent. And I'm going to get 16 and negative 13. Okay? So this means that the coordinate vector xc, okay, the coordinate vector x with respect to basis C is going to be 16, negative 13. Now, I have this change of basis matrix I found, okay? So if I take this coordinate vector and I take this matrix I found, okay? So P, again, that goes from B to C is equal to 6, 4, negative 5, negative 3, okay? So we found when we did this row reduction, okay? My coordinate vector x, my coordinate vector with respect to x for B is 2, 1. So if I go through and multiply, I get 2 times 6 is 12, plus 4 times 1, I get 16. And 2 times negative 5 is negative 10, plus 1 times negative 3 is a negative 13. And so you notice by multiplying by the matrix, I got the same thing, which didn't require the row operations or the calculator work here. I could just multiply by this matrix and get my new vector, okay? So that is the benefit of a change of basis matrix, okay? So you want to row reduce with respect to each row, and then apply that matrix by multiplication to the vector you're looking at. So a couple of things to note here. The columns of a change of basis matrix have to be independent because it refers to a basis, okay? So these columns have to be independent, okay? When we talk about this row reduction up here, these are the C coordinate vectors in B, okay? C coordinate vectors, C hyphen coordinate, okay? And we're going from B to C. So when you see this coordinate vector notation, we're taking the basis vectors in B and going to C, B to C. So that's the change of basis matrix. Here goes B to C. And again, we write it on the right, so we know to put the B vectors that we're starting with on the right and the C vectors in that basis that we're changing to on the left. So B to C or U to V, or, you know, you can read them from multiple places here, B to C, U to V, W to X, etc. Okay? So that is the last section of chapter 4. Okay? If you have any questions, please get in touch by email, stop by office hours, whatever means works for you. You can use the help features in the My Math Lab homework, including there's an email your instructor. feel free to do that. If you need some help, I'd be happy to look into it, see if I can get you on the right track. And if we need to set up a time to meet, we can figure that out as well. Be mindful of quizzes, homework, checks for understanding, tests. Check a look at those calendars and checklists and make sure you're getting to everything you need to get to. So we just have 2 chapters left. That's chapter 5 and chapter 6. We shift gears just a little bit to talk about eigenvalues. We're still talking about linear systems, still talking about the operations, so forth. Chapter 5 deals with the eigenvalues and eigenvectors. We'll explain what those mean when we get there, and I'll see you then in that next video for chapter 5.